Thank you. So my name is Erik, and I'm a software engineer at the Red Hat's Emerging Technologies group, where I work on tooling for allowing people to run insightful, data-driven Spark applications in the cloud. And occasionally I get to do some internal data science consulting. So why are you interested in data sketching at all? The basic goal of all sketches is to maintain a data structure that's fast to compute and fast to operate on, that is much smaller than the actual data, but that actually preserves all of the essential features of the data. I'm curious, show of hands, how many people here have done data sketching? Okay, a few people. I think even if you answered no, it may be the case that you actually have done data sketching but didn't know it. If you've ever taken like the mean or variance of some numbers, you've done a sketch of your data. If you've clustered data, the centers of your clusters are a kind of sketch. And even if you've trained a learning models basically encode a kind of compressed representation of the training data. And so learning models are actually a sort of data sketching as well. So the sketch I'm going to be presenting today, the T-Digest, was introduced in a paper written by Ted Dunning and Omar Erdl, computing extremely accurate quantiles using T-Digests. You can see Ted Dunning's GitHub site up there where he has code and actually the copy of the paper itself in GitHub. And there are other implementations. There's implementations in Java, Python, R, JavaScript, C++, and Scala. So what kind of a sketch is a T-Digest? Its inputs are essentially any sequence of numeric observations. In fact, they're actually formally paired, numeric observations paired with a mass. I'll be referring to it as a mass, but you can think of it really as a frequency or a weight. And the actual sketch is an estimate of the distribution of all those observations. Specifically, it represents it as a cumulative distribution sketch. One nice thing about them is they work with incremental updates. So if you have your current T-Digest, you can send in these observations and get an updated T-Digest. This is excellent for larger streaming data because you can just take your fire hose of data and aim it at the T-Digest, and you don't have to save your data. It's just all you have to actually save is the running sketch of your data, which is, of course, much smaller. So what's the actual benefit of doing any of this? Just a brief example. Suppose you have a REST service and you're running queries against it, and you're collecting some telemetry like the actual query latencies. If you take your query latency stream and create one of these T-Digest sketches, you can answer all kinds of interesting questions like, are 90% of my latencies under 1 second? Or what does the actual distribution of latencies look like? You can plot them. And you may even want to take this information and simulate your latencies. So you can use the information in the digest to simulate the data instead of just collect it. So how does it actually represent the distribution? Under the hood, it basically stores a bunch of what are called clusters. And all a cluster is a location and a mass. And the location represents basically a location somewhere in your data space. So I draw them, for large masses, it's big circles, and otherwise they're smaller. When you update it, you have an incoming observation, and all you do is you locate the cluster in the T-Digest nearest to that observation. In this case, it's the green one. You add the mass, and then you also update the location based on the weighted average. And at this point, I'm going to make a little observation. You can see that I drew the incoming observation as another cluster. And you can see that because the observation is also basically a location and a mass, your incoming observations are the exact same thing as what's being stored under the hood for the T-Digest. That's going to come back later. Each cluster can be assigned a quantile, and all that really is sort of like the sum of the mass to the left of your cluster divided by the total mass that's being stored. So that information is actually used in the formula for setting maximum mass bounds per cluster. So the Q times 1 minus Q term there provides the shape of that curve. It has its maximum in the center of your data, like near the median, and towards the edges of your data, it's small. The term M is basically just the sum of all the masses, and so what that does is the more observations this thing has seen, the larger it allows the clusters to become. And then the C term is actually a free parameter you can supply for compression, and the larger you set that, the larger it allows the clusters to become. So these bounds can force new clusters to be created. Suppose you have an incoming observation and it's saying, hey, can I merge with you? And the cluster basically says, well, if I do, I'll be over my bound. And so, it basically takes as much mass as it can up to its bound, and then the remainder is sent to a new cluster that's being stored under the hood. So why is this happening? The reason it's happening is because it wants to sort of enforce smaller clusters at the edges of your data. The reason for that is because the edges of your data are where your distribution tails might be. And so for your tails, you really want to model them with fidelity using small clusters, not big fat clusters. And then in the middle, it allows substantially larger clusters. So T-digests act like monoids. How many people here actually know what a monoid is? Oh, okay, a few people. If you don't, it's not a big deal. Really all it means for our purposes is that you can take two of these T-digests and then just combine their clusters, as you see in the middle, and insert them into a new empty cluster to get a new combined cluster that represents the data that was present in both of them. And recalling my little observation that the observations have the same form of clusters, this is very convenient because all you really do is take those clusters and insert them straight in as new observations to your empty cluster. So it's actually efficient and elegant. So this is where the rubber really hits the road for Spark. Because these things can be combined in the way I just described, you have data in Spark which resides, of course, in multiple partitions. And so you can map each partition independently in parallel to one of these T-digests, and then at the end combine all those T-digests for each partition into your final results. So you're basically doing MapReduce in the parallel way that we've all come to know and love. So there's different ways you can actually define this operation, and they all have to do with how you insert those clusters in the way I was just describing. The first one, which was mentioned in the original paper, was basically taking them randomized order. So you combine them, just shuffle them, and insert them that way. The way it's actually happening in the implementation on Ted Dunning's site right now is it takes them in the location order. So you basically take them in the order that you can see here in the spatial order and then insert them. There is a third way that I stumbled over while I was trying to fix the problems with the randomized order, where you take them and then sort them from large to small mass and insert the largest ones first down towards the smallest. So why does this matter? If you take some data and run an experiment where you know the answer, you know the distribution that your data is supposed to have, and you run a bunch of these combinations, you can track what's actually happening, how close are the results to the original distribution. And if you make the plot, you can see that the random order actually has a problem. It's like the more of these things you combine, the worse it gets. It's drifting farther and farther from the distribution. So to fix that, I created the large to small ordering, which is the orange curve down there, and it got basically just better and better, so it converges. I then was talking with Ted Dunning, and he showed me about the merge algorithm, and I ran the experiment again, and it also converges. So basically, both of those methods are good, and you just don't want to do it randomly. So some algorithmic considerations. The clusters have to be maintained in sorted order. They are frequently inserted, deleted, or updated, and you have to always be able to query every incoming observation to the nearest cluster, and you also need to be able to query a prefix sum for these things because you're actually getting information about the cumulative distribution. And you really would like to do all this in sublinear time. So I chose to do this in my implementation by storing all these things in a balanced tree, like so. And fundamentally, they're stored in location order, spatial order. So some actual Scala considerations when I implemented it. That balanced tree, I used a immutable red-black tree. It extends a map and map-like, which if you work with Scala, you're probably familiar with. So you can do all of the standard map operations. And I implemented some of these other capabilities as basically mixable traits. So the red-black feature, the ordering, the ability to increment the values, nearest neighbor searching, and the prefix sum are all capabilities you can mix and match, keep what you want to create new versions of these data structures. I also wrote an interface that allows it to be used with the algebra monoids and aggregators. An experimental feature I've been messing with is that I'm leveraging the idea that these are actually just all sitting inside a map. So if your data is under the hood discrete, you can basically keep discrete values and just increment the frequencies up until some maximum number. And if it grows beyond that, you can fall back to the more traditional numeric update that I described already. There are lots of applications. You can do quantile estimation with them. I'll be showing that in a minute. You can use them to characterize your feature data if you're doing training. You can use them to build codecs. Most encodings leverage distribution information to optimize, encoding losses. You can do things like value at risk modeling, which is predicting future returns on stocks. So you can use these to accumulate a sketch of like past behavior of your stocks. And if you need to do generative models, you can actually very easily use these to do that, and I'll show you that in a demo as well. So I'm going to skip to my demo here. Hopefully it will work. So I'm going to go back to the example I was talking about at the beginning. Imagine that I have some query latency data, so I'm going to load that in into an RDD, and I can see how much data I actually have. And it's yes, a million observations on latency data. And that's got a certain number of partitions as well. So it's stored across 10 partitions. So I'm going to actually compute a t-digest on these, and I'm going to use the Spark RDD aggregate method. And start with an empty t-digest, which is configured with a little compression factor there. And for the accumulation stage within the partitions, I'm just adding in the data and doing the incremental updates. And then at the end, I'm using that monoidal combination to combine all the 10 partitions. And so there Spark goes. And it's already done. So I can ask myself, what's the actual size of this cluster? Oops. Just do it this way. And we can see that it's actually modeling the distribution of those 1 million observations with fewer than 1,000 clusters. So it's definitely keeping a very compressed representation. I can actually plot them as I discussed. Hopefully I resized this correctly. Oh, good. So on the left, you can see that there's the cumulative distribution, and on the right is, I used a little math to show a plot of the actual density distribution. So as you can see, it's got a mode right around 0.2, and then that tails off to the right. At this point, you're probably all thinking to yourselves, this guy's really retro using ASCII graphics. But that's wrong. I'm actually retro because I'm using RDDs and not data sets. So I talked about quantile estimation. So that one question I asked at the beginning is like, how many of my observations are under 1 second? So you can obviously answer that easily with a cumulative distribution. And so it turns out that almost 96% of them are underneath 1 second latency. So if my threshold was to be under 90, then I'm doing really good. And then I can do the reverse. And say, well, what is the 90% quantile? And it turns out that it's about 0.78 seconds. So basically, 90% of my latencies are under 0.78 seconds. And I talked about generative models. So suppose I wanted to use this thing to simulate. So I'm going to create 10,000 simulations. And some of you may be familiar with the little trick. If you actually have a cumulative distribution, you can invert it on a bunch of data drawn from a uniform distribution and get basically simulated values. And so I'm going to do exactly that. And I'm going to see how close it was to my data. So plot a couple histograms here. And yes, good. They both look almost exactly the same. So that was those are the things I wanted to demo. And that's the end of my talk. You can get my implementation of this up on this ISARN project. The URL is right there. And that was all I had to talk about. Are there any questions?
Cool. Let's give him a hand. All right. With that, we can drop into some questions. Go ahead and raise them up high, and I'm happy to go around. All right. Pretty straightforward. So are you going to change at all the implementation to like do something like data sets? I mean, I realize it's on RDDs and you can kind of specialize some of those aggregation functions at like a lower level. But yeah,
well, actually, that was Spark's function. That was aggregate. So if there's an aggregate method on data sets, it would already work just pretty much exactly the way I did it. But if there was any actual additional code that I would need to write, I would be more than happy to do it.
Gotcha. Cool. Is it published as like a Spark package or anything like that?
It is not published as a Spark package. It's not, as you can see, it's not really especially Spark specific. So yeah. I didn't do that. Like I said, I did write a little interface for, Algebird. If there was anything, I mean, I could actually write some special helper functions for Spark. I would be more than happy to, or if anybody else wanted to contribute. I'm not entirely sure it's necessary, but
yeah, no, for sure. Probably cross that bridge right there. All right, cool. Oh, nice. We got a question.
On the same theme, right? So do you have a UDAF which wraps this T-digest, or are you just using a RDD API to just simulate and demonstrate this?
Can you repeat the question?
Well,
I'm
on
not
the
sure.
same lines, right, about actually creating a Spark package with a UDAF function, like an aggregate function in Spark,
Oh, okay, yes.
to
yes.
actually wrap this, because I've done some of this stuff, and I had a conversation with Ted Dunning also. And there's some areas where the Spark interfaces actually doesn't really help when you're starting to scale that. So I was wondering if you already have something out there, and if you do, then I would like to try it out first of all, and if not, then maybe collaborate with you. So I was wondering if you have a package out there, or...
I do not have a UDF package, so if you have an interest in that, that would be fantastic. Yeah,
Cool.
I'd be happy to work with that.
Awesome.
There we go, community at work right there. That's awesome.
I have two questions. The first one is, do you have any sort of idea of a way to get confidence intervals for the inverse distribution?
I do not have a way. That's an interesting question. I mean, obviously, if you know the answer, you can do something like, Kolmogorov, Smirnov statistics on it, and get a confidence against like how likely it is to be similar to something else. But since you're taking, what you're basically storing is frequencies, so I can imagine that conceivably something even like chi-squared might be applicable there.
Yeah, it kind of seems like if you try to get the 50th percentile, the range of actual values it could really be seems like larger than just a point estimate.
Yeah, that's actually a really interesting question, and I'm not really going to pretend to have a coherent answer, but I'll think about it.
Okay, my other question was going to be, instead of having almost like a normal distribution of the quantile accuracies, could you just sort of have an exponential, so you don't really care about the low level accuracies, but you want more information on the like 99th percentile and higher?
Right. I think you could actually do that. I mean, I've had all of my unit testing tested things which were like two-tailed or single-tailed, or even like I did a uniform which has no tails at all. And allocating the little extra bit of resolution towards the edges, even if you don't need it, doesn't seem to hurt it at all. But if you ever determined that for some reason you really wanted to like make sure it was only doing it at one end or the other, you could probably modify that bound curve that I showed to do that. To the extent that I've worked with that, it's basically not necessary.
Cool, thank you.
Yeah.
All right, I think with that, we will call it for this talk, but let's give him another round of applause. That was great.